Nature is made possible by public television stations, your gas company, and the gas industry, whose respect for nature and the environment is reflected in the underwriting of this series. America's gas industry provides 160 million people with natural gas energy all across the country.
A home has become much more to us than a shelter from the elements. But it is our ability to build structures suitable for any environment that has enabled man to live virtually anywhere in the world. Hi, I'm George Page for Nature. We tend to think that this ability sets us apart from the rest of the animal world. But nature abounds with examples of ingenious design that allow animals to survive in otherwise hostile environments. Whereas man has developed basic engineering principles, animals rely on thousands of years of evolutionary invention and selection. Surprisingly, this approach is so successful that virtually the entire spectrum of building skills which man, the engineer, has devised for himself is reflected somewhere in the natural world. For example, the honeycomb. We take its repetitious pattern of hexagons for granted, but it's a model design for combining lightweight with incredible strength. It does this so well that during World War II, a material based on the honeycomb was actually used in the building of warplanes. It does much more than provide a structurally safe home for the bee colony. It also acts as a natural air conditioner, keeping temperatures during the hot summer months low enough to avoid the disaster of a beehive meltdown. And without this simple yet elegant design, the complex and dynamic social life of the bees simply would not be possible. This time on Nature, our film explores the strange and wonderful world of animal building technology. Animals build for somewhere to live or to raise their young, to catch prey or store their food. With unusual materials, they create their version of what we call home. By building, these wasps change the world in which they live, and they face the same kind of problems as human architects and engineers. Over the eons, they've selected new materials and developed new structures. They must build to survive. The first social bee's nest appeared about 60 million years ago, but life on Earth then was already old. The earliest animals lived 1,500 million years before the birth of the bees. The cradle of life was water, a medium that was kind to the first life forms, supporting their weight, cushioning them from the hostile atmosphere above. In this first home, soft-bodied creatures like the sea cucumber had little to fear from the climate, but the water soon became a place where animals were in need of protection from one another. A crab, even with an armored shell, seeks further security from its enemies by digging into the sand. But there's another way to hide, and that is to rearrange the environment in a lasting way. In other words, to build. Mantis shrimps are accomplished builders. The burrows they excavate are permanent shelters, which need constant maintenance to keep them clear of drifting rubble. Altering the world about them costs time and energy, but the gain is safety. For the mantis shrimp, it's well worth the effort. Even the smallest animals find safety in building. This tiny amoeba is 1/10 of a millimeter long and constructs a minute case of sand grains around itself, a protective capsule in the depths of inner space. Surprisingly, animal building may be as old as the first one-celled creatures. This single cell has no nervous system and only arms of jelly. Yet it can gather up just the right number of sand grains of an ideal size and cement them into a protective case. Sharing this watery world, and not much bigger than the amoeba, is a creature known as the rotifer. It feeds on tiny particles in the water, and the undigested waste it makes into round pellets, which it sticks together to form its own protective cover. The uniform shape of the pellets is an advantage when building. Like bricks, these standard units, simply arranged, make a neat structure. The tiny rotifer can lie inside the tube, exposing only its two wheel-like filters. On a grander scale, a caddisfly larva builds a case of stones, local materials found quickly and easily on the stream bed. A stone is examined and, if acceptable, is stuck to the front of the tube using silk secreted through the mouth. Stone cases can be very heavy. Carrying around such heavy armor like a medieval knight has disadvantages, but not unless its enemies invent the equivalent of gunpowder is it likely to give up its stone house. Sand grains come in all shapes and sizes, but the caddis selects just the right type it needs and fits them very precisely. The result is a stone mosaic set in silk. Some kinds of caddis larvae use leaves, cutting pieces to an exact size. As in prefabricated buildings, such pre-shaped material makes construction easier. But will they pass the building inspector's test? The dragonfly larva's aim must be on target. It must seize the caddis head before it's withdrawn into the security of the hard case. The jaws are useless grinding on stone. A house made of vegetation seems an easier target. The plant fragments are flexible, and the dragonfly larva tries to squeeze its mouth into the entrance to grab its meal. But even in this predicament, the caddis is likely to survive if it can retreat far enough into the case. A direct hit, disaster for the caddis, but succulent success for the attacker. Agile creatures like the sea stickleback can use their speed and agility to evade predators, but they set aside a defense budget to protect their vulnerable young. The male builds a nest of seaweed, bound together by a continuous tough strand secreted from its kidneys, a waste product used as a cheap building material. The fish is hooked, but on a line of its own making. A firmly fixed anchorage is essential for this tensile thread, wrapped round and round the nest in which the female lays her eggs. Safe within this basket, the eggs are gently fanned by the male to keep them supplied with oxygen. The ability to assemble naturally occurring materials is not a talent for which mammals are renowned, except for humans and beavers. The beaver builds two remarkable structures, a lodge in which it lives and a dam to create an artificial lake. The lake is used to store branches. The nutritious bark will be its winter food. In northern latitudes, the problem of surviving the freezing winters has forced the beavers to take control of their immediate surroundings and create these ponds with dams. The dam is made solid with sticks and plants carefully worked into position and sealed with mud. The beaver uses the sound of running water to guide it to where the material should be placed on the dam. Branches are used where the gap is wide and the noise of rushing water is loud. Mud and fine materials are brought along in response to a mere trickle. The beaver's dam must support its own weight, but much more importantly, it must resist the tremendous push of the great volume of water held upstream. The downstream side is strongly buttressed with branches. The beaver is an efficient lumberjack, felling both timber and food. The leaves of aspen are eaten now, but many branches will be stored underwater for the winter. The massive log house is sealed with mud, and inside the family is snug and secure. These living quarters are well ventilated. The branches forming the roof are arranged loosely. The only way into the lodge is by underwater tunnel, an access that remains free of ice all winter. Their skills and lifestyle make beavers unusual rodents. Most other rodents live entirely on land, either on the surface or burrowing just beneath. In spring, wood mice forage through the undergrowth in search of food and nest materials, which they return to their underground home. The wood mouse burrow is usually a tunnel dug around the base of a small tree. From this main tunnel, it digs two or more side tunnels upwards and outwards to the soil surface. Another subterranean corridor leads below the tree roots to a nest chamber and a storeroom. The leaves they gather provide superb insulation. Piled together, they form a warm nest. Unlike the wood mouse, the mole spends most of its life in its tunnels. Almost blind, but with powerful shoulders and spade-like front paws, it's perfectly designed for burrowing and quite unsuited for life above ground. The mole digs several kinds of burrows. The nest cavity may be a yard or more deep, while its surface tunnels form those soil heaps hated by gardeners. The tunnel is both home and a place to hunt earthworms and insects. The elegance of the mole's design as a burrowing machine shows up again in a quite different creature, a mole cricket. It's an insect and another expert digger. It has mole-like front feet, even the same nervous energy. But most remarkable is the way it specially shapes the tunnel entrance and therefore amplifies and directs its courtship song. The similarity between cricket and mole suggests there may be only one way to design a digger. But these many volcanoes erupt from the tunnel of a burrower that's completely different. These creatures live underground in the warmth of the Kalahari Desert. They are naked mole rats, and their teeth are the special digging machinery. Teeth so enlarged that the lips cannot close over them. Naked mole rats are very sociable. They never dig alone. While one miner is at the work face, others push soil backwards down the tunnel, and those looking for new loads move forward, squeezing over their backs. It's a conveyor belt of mole rats. Nearly 2 miles of tunnel can be dug in the search for fleshy plant tubers, their main food. Their bizarre social life is more like that of termites than other mammals. Colonies may contain 250 individuals. They even have a queen, the single large reproductive female, secure in their underground chamber. Another digger is this wasp. It can burrow in hard-packed desert sand, digging with its front legs as well as its jaws. Just a simple hole in the ground will provide a safe haven for its young. Once the burrow is ready, the digger wasp then searches for caterpillars. Paralyzed by a sting, the caterpillar will remain fresh for some time and will be food for the wasp's grubs. The simple hole becomes both pantry and nursery. When fully provisioned, the hole is sealed. Finally, a lump of sand held in the jaws is used as a hammer to pack the loose fragments tightly and camouflage the entrance. Going underground is one way of safely housing and rearing young, but there are other solutions to that problem. Birds are versatile builders when it comes to ensuring the safety and comfort of eggs and chicks. Many large birds, like the South American black-necked swans, build a nest which is just a pile of feathers and bits of plants, insulating the young from the cold ground. Mute swans also show the virtue of this simple technique. There is little effort required, and the reeds are readily available. With simple movements, he passes, she places. In lakes high in the Andes of South America, giant coots use this straightforward method of collecting and dropping to create large platforms to nest on. The work is time-consuming and more demanding in effort, since the vegetation must be brought from a great distance. But it's worth it, as the artificial islands will keep the young safe from predators on shore. The buff-necked ibis is another bird which simply stacks its nest material. It uses twigs. This is generally how we like to build, ground up and resting on firm foundations. But why doesn't the pile explode outwards and collapse? No glue or knots hold it together. Rooks face a similar predicament. Their nests should fall apart, but they don't, and the reason is that each twig is carefully placed. A rook doesn't just throw one twig on top of another and hope. On the contrary, it seems to work very hard to get everything just right. The idea is to fit the twig so that as many as possible of the bumps and projections catch on to other twigs. From the ground, a rook's nest may appear as a rough structure, and in a sense it is, but several different layers can be identified. Its base contains the thickest twigs, and on the inside wall, rooks use the more elastic twigs of birch and willow when available. When the nest is nearly complete, soft turf is gathered to line it. For smaller birds unable to lift large weights, the piling up technique of building is rare. A house martin's nest has no support underneath, which raises different engineering problems. They build with mud. Back at the nest, the mud is applied with rapid paddling movements of the beak. This removes air bubbles and welds the new load to the nest. Bits of straw are also picked up with the mud, and not by accident. When straw is added, it stops cracks from developing and the nest from collapsing. Saliva is also worked into the mud with the tongue, possibly adding additional strength. In these caves in Southeast Asia, some birds use saliva in an extraordinary way. Cave swiftlets build their nests using saliva which emerges from the mouth as a glutinous thread. Soft when extruded, the saliva rapidly hardens, and the bird's own feathers are incorporated into the matrix of saliva to form the nest. Astonishingly, in the same cave, another kind of swiftlet builds its nest out of strands of saliva alone. In engineering terms, these nests function like cantilever beams. They're attached at one side with no support above or below. Interestingly, when the nest is boiled, it makes a Chinese delicacy, bird's nest soup. If their nest is removed, they will build a new one immediately. When dry, this pure saliva nest can take the weight of the whole family. The strands of saliva have great tensile strength. Other birds use the tensile properties of cellulose and plant fibers to hang their nests. A pendulum tit lashes its nest foundation to a forked twig. The material is a yarn spun together from the hairs of seeds. As building progresses, the fibers form a soft framework around a closed nest chamber. The weaver birds of Africa are the master builders of the bird world. The black-headed weaver anchors its nest on a bare twig. To weave, the head pushes and pulls the beak like a needle through the nest fabric. A good needle is essential for any basket weaver. The weaver's needle must be able to move in all directions. The bird can achieve this with its very mobile neck. Another prerequisite for success is the ability to follow the same strand as it's worked through. Sharp eyesight is all that's needed here, and the bird has it. In fact, many kinds of birds possess all the equipment to be excellent weavers, and it's curious that relatively few practice the craft. A fresh green leaf is supple, ideal for weaving. Its strength is in its cellulose fiber, and when dry, it forms a firm nest, able to withstand considerable strain. In Africa's Kalahari Desert, many trees become draped in huge haystacks, built not by weaver birds, but by sociable sparrows. Each bird collects dry grass to contribute to a communal structure. One haystack can contain 100 nests. The sparrows just push each grass stem into the stack. They are thatchers, not weavers. The Kalahari can become quite cold in winter. Protected from losing heat in these nests, birds are able to keep breeding throughout the cold season. The result is a thriving sparrow population. The investment of effort in building is great. One haystack can weigh as much as a ton. But the last straw may break the branch's back. Such a narrow structure can take a big load, but if overstressed, it will collapse. Here, a thin strand of slime supports the great weight of 2 mating leopard slugs. This mucus secreted by the slugs is elastic and bears the entire load. Isolated in space, the slugs can mate undisturbed. Not until the invention of steel cable were human engineers able to exploit fully such a tension structure. Human or animal, such devices are not complicated. They have 2 basic features, a cable and an attachment point. Here, a dab of slime. Spiders were ahead of the engineers by millions of years, not with steel cables, but with silk. Tough and versatile, each spider's silk strand is as strong as nylon and has twice as much stretch. The main support cables of the web must be firmly secured to twigs and leaves. Spiders build many kinds of traps. The function of this orb web is to bring flying prey to a sudden halt and prevent its escape. Here, the spider is spinning its sticky capture thread, which is supported on a non-sticky frame of strands radiating from the center. The radial threads are elastic. If stretched and let go, they return to their former shape. So they can blow about in the wind without damage. The capture thread is decorated with chains of sticky droplets. These semi-liquid beads of glue adhere to the prey on impact and spot weld the victims to the web. These webs are sophisticated traps. Their finest feature is the ability to absorb the great shock as prey collides. But sometimes, jumbo-sized flying objects strain the silken scaffolding to the breaking point. Here, the outcome is disaster instead of a delicious meal. At home, on the edge of its web, the spider keeps in touch with the action. A leg on the communication cord monitors vibrations and lets it know whether the catch is large or small. A hoverfly is quickly wrapped in a silken shroud and injected with venom. Trussed up, it will be stored until the spider is hungry. Capture webs and spiders come in all shapes and sizes. The ogre-faced spider hangs from a simple array of threads and holds its little web delicately at the corners, ready to thrust it down on the insect traffic passing below. However, deep within the heart of the Malaysian rainforest lives the master architect of the spider kingdom. Like most spiders, it uses concealment and ambush as predatory techniques, yet it raises them to an art. Appropriately called the trapdoor spider, it utilizes up to 12 communication cords, radiating from the lid of its concealed tubed web. Delicately grasping these tripwires, she feels the telltale vibrations of prey. Seldom seen, trapdoor spiders are found worldwide, equally at home in deserts as well as the forest floor. Constructed of webbing, spittle, and earth, the trapdoor lid is perfectly camouflaged. It seals out rain and heat. Beneath the lid, the spider's tubed home may reach a foot or more in length. This forest ant seems to be testing fate. And indeed, not every attack is successful. Again, the spider lies in wait. And the ant returns, but it's well protected with a repellent mantle of formic acid. The caterpillar has no such defense. Not only spiders are able to spin silk, some ants make homes of silk in the branches of trees. Generally, the silk is used to bind leaves together into a purse. Teams of workers span the gap between leaves, their legs and jaws straining to hold the edges in position. The adult ants don't secrete silk. Only the larvae do that. So the adults pick up the white grubs and, using them like a tube of glue, spin the threads back and forth across the gap. Silk is used in many ways. Even caterpillars find alternative roles for it. Under the sheltered bank in a Malaysian forest, a tiny cage envelops the chrysalis of a moth. This is a cocoon built by a caterpillar, the material all of its own making. Hairs plucked from its body have been carefully arranged and stuck together with silk. No one has yet seen this being done. It's probably designed to protect the chrysalis from marauding ants, as is this strange shell-like cage built over a plant-sucking bug. The material secreted from the back end of this animal is a wax of some kind. Plant-sucking bugs excrete masses of honeydew, but some bugs, rather than wasting the sugar, convert it into wax. This architect makes the wax into an impregnable prison cell within which it can feed unmolested. A basic building substance like wax and the technology of its use has been an essential factor in allowing the social bees to develop some of the most intriguing structures in all of nature. This is the entrance to the underground home of tropical stingless bees. The long, narrow tube is easily guarded against attack by ants. The airspace around these elaborate nest entrances is patrolled constantly by the bees during daylight. Beeswax is normally soft and malleable, but when mixed with plant resins collected by the bees, the wax becomes hard, allowing the erection of these impressive towers. The substances mixed with the wax are taken from a variety of sources, including the surface of leaves. Deep in the interior of the nest is another, darker world. It's not the familiar honeycomb. In these stingless bee nests, the cells and food storage pots are wax globules attached to one another by connecting struts. Everything is firmly fixed to something else. The different colors may reflect age or the quantity of plant resins mixed with the wax. Wax has had a considerable influence on the life of the bees. Its development made possible the leak-proof honey pot. This allowed a high population to live on stored food through lean times. Damaged trees are also visited by the bees to gather cellulose fibers. The bits of rotten wood are packed onto the pollen baskets of the bees' hind legs. The shape and color of the nest entrance is characteristic of each type of stingless bee. But just why they create such ornate portals is a mystery. Perhaps they improve air circulation to the nest interior, as well as making it easier to defend against attack by small animals. Buttressed with wax at its junction with the tree, this light, long cylinder proclaims its great strength by projecting outwards. Besides wax, other building materials have influenced the social lives of insects. Among different wasps, a clear succession of technical advances has echoes of our own industrial revolution. This solitary wasp is shaping a mud pot in which to rear a larva. It vibrates its abdomen rapidly to spread the mud. The potter wasp spreads mud with its jaws, assisted by a buzzing vibration of the whole body. This helps liquefy the mud during spreading, removing cracks and bubbles. Nearly all species of solitary wasp either build mud cells or dig burrows. But here's an advance. This wasp is social, and in nesting it uses a new technology, paper, and its invention has changed its lifestyle. Paper is a plant fiber embedded in a matrix of saliva. Like the silk thread or the steel cable, it's a tension material. Weight hangs from it. The paper in these cells is light but crumbly and weak. It requires additional support, such as a plant stem. But it was a beginning, and as social wasps evolved, their technology advanced with them. Such nests are very exposed. These tropical Asian wasps repel ants with a secretion used to form a protective ring around the plant stem above the brood cells. It's known as the ant guard. The wasp is meticulous in looking after the ant guard. Fresh secretions are applied often and can build up into a neat spiral. Ants sense food, but soon give up their attempts to cross the chemical barrier. Another kind of wasp applies the ant guard directly from her abdomen. Here, the nest design is quite different. Composed of plant fibers mixed with water and saliva and known as carton, it has room for 10 cells and 2 or 3 adults. All these small wasp societies build their homes on hanging stems or rootlets to reduce the risk of predation by ants. Not all produce such elegant paper palaces. Caves offer natural shelter from wind and rain, and many wasps take advantage of this. Inside, the roof is encrusted with nests built in various styles. A simple, flat comb attached directly to the roof. But the sticky ant repellent must still be coated on the inner walls of the cells. Several wasps sitting on the comb are additional protection for the eggs and larvae. Although in the cave, they're still very exposed in these open cells. If the comb is left unattended or without chemical protection, the brood will certainly be taken by marauding ants. What was needed was not a palace, but a stronghold of paper. Packaging the brood in carton envelops the young and keeps out the ants. The only way in to this concealed colony is a stylish spout. And other enclosed paper nests also occur in this extensive wasp city. But all are small, fragile dwellings. The number of wasps per colony is low, no more than around 10 on each nest, which is as many as the weak paper can support. So how did their nests get bigger? Outside the cave are wasps with a possible answer, those that hang their nest from a leaf by a narrow stalk. A simple device, but one unknown to the primitively social wasps inside the cave. Its invention gave the brood of these Palestine wasps greater protection from ants, which cannot cross the ant repellent stalk. The new nests were getting bigger and heavier, and that was only possible because the paper used was much better and stronger. Eventually, very large combs could be suspended from narrow stalks. The light, strong paper was to prove just the right stuff to build bigger structures housing even larger social groups of wasps. Hidden in your own garden or attic, such a stalk may be supporting a stack of combs hanging one below the other in the nest of the familiar garden wasp. Its paper is strengthened by the woody fibers scraped from fence posts and other pieces of unrotted wood. There is no great threat from ants here, but the huge brood must be protected from the cool summers. So the combs are wrapped in layers of insulating paper. So paper made possible the rise of the wasps. But even their crowded citadels are dwarfed by the colonies of the termites. With millions of individuals in one colony, termites form the largest insect societies. Out of their nest, termite trails are covered, but if exposed, they become easy prey. Wasps are carnivorous and frequently make a meal of termites. But as 1,000,000 are eaten, so 1,000,000 take their place, as these invincible armies march to and from the most remarkable homes in the animal kingdom. Some termites build their nests in trees, the material again a kind of paper. Others construct towers of mud on the forest floor. Inside, the mound teems with life, a fortified factory for the production of termites. In its temperature-controlled, air-conditioned interior, plants are composted, fungus is grown, and baby termites roll off the endless production line. The castles of the termites reach out into the forest and over the trunks of trees. Through covered walkways, the termites stream unhindered, and in their millions unobserved, intent upon their quest for food. The slightest damage reveals this termite traffic. At once, repairs are called for, and from among the horde come workers to seal the gap and soldiers to patrol the breach. With their syringe-shaped heads, the soldiers can squirt a sticky liquid which entangles their victims. The workers use two quite different building materials, wood fibers carried in the mouth and a glue squirted from the rear end. The sticky excretion will set hard. The wood fibers worked into it make it a reinforced cement. The ability to build and efficiently repair the avenues of the extended termite cavity ensures the safety of its busy inhabitants. Across the face of the world are scattered the homes of animals, defenses against heat, drought, deluge, famine, and theft. A communal home or a private retreat, they were formed from the fabric of the planet in designs and materials that foretold man's own remarkable age of architects. In just 100,000 years, the dust of the earth was shaped into the cities of our world. And who knows what will be the shape of things to come.
Nature is made possible by public television stations, your gas company and America's gas industry, supplying natural gas across this land of ours, providing gas energy to fuel industry, warm homes, heat water, and cook meals for over 160 million people from coast to coast.